sense that if you put your thumb in the z direction of your right hand and your fingers in the x direction, when you close your hand, the fingers will go to the y direction. Right? This is in comparison to one where the x and the y were changed, in which case it would be a left-handed system. If you put your fingers in the direction of x and close them, you would have a left-handed system. That if you put your fingers in the direction of x, if this were x, and close them, they would close in the direction of y. Here, a right-handed system closes in this direction. When you close your fingers, they go from x to the y direction. Another example would be this, right? And perhaps this seems like as if it would be more natural. Then we'd put x here and y here in their usual position, and z coming out from the board. This is also a right-handed system. X, close your hands to y, and your thumb is pointing in the z direction. This will be used sometimes, but this is more standard. And part of the reason for that is, one of the things we're going to want to consider is when z is a function of x and y, so that for each point in the xy plane, we will have a point z above it or below it. Now, with each point, in three-dimensional space, we're going to want to associate with that point three coordinates. By drawing this rectangle, like so, whose, well, this rectangular parallelepiped, whose planes, surface edges here, their surfaces are parallel to the xz plane, which is designated by the x as the xz plane. The xy plane, that's the horizontal one. It's written as the xy plane, and the yz plane. The yz plane is the one that's on the blackboard here, so to speak. Right. And what we wish to do then is with a point, we wish to associate three numbers. Right? The first is going to be its x-coordinate, and that's going to be where this plane here intersects the x-axis. Right? So if this is the point here, ABC, and this point over here is distance A away from the origin. This is also called the origin. This one is distance B away. So say this distance right here is B, and this one is distance C. So, like so. And then, as a consequence of this, every point in three-dimensional space will correspond to a triple ABC. And conversely, if one has a triple ABC, you can find the point in three-dimensional space corresponding to that triple. So that, for example, this right here, if this was 1 unit, and this was 1 unit, and this was 3 units up the z-axis here, this point here would then be the point 1, 1, 3, 2, 2, 3. If this was 2 units, and 3, it would be 2, 2, 3. That would be this point right here. Points whose coordinates are all positive are said to belong to the first octants. These three planes divide space up into 8 different parts, and the one here where all of them are positive is called the first octants. Right? The other octants are not really distinguished. That's to say there isn't a second and third octant, although you clearly could do that if you wished to. These points are not all that particularly easy to graph, but for example, if you wish to indicate where a point is, you can draw in the rectangle, and so this point here would be where x is equal to 2, and y was equals to, let's say, minus 2. Perhaps x is 2 here. Y is perhaps equals to minus 2, And z is equal to minus 2. So this would be the point 2, minus 2, minus 2. Okay, we're going to want to get distance in three-dimensional space. And so if we have a point here like this, right here, and this is the point x, y, z, we want to first of all determine the distance from that point to the origin. This distance right here, right? And that can be obtained by noting that this right here is a right triangle, right? This distance right here is, if this is the point ABC or XYZ, if this is XYZ, then this distance right here is absolute X, right? Absolute X is the distance, XYZ, putting this in a standard coordinate system. Absolute X is the distance to the YZ plane. Right? This distance is absolute X. This distance right here is absolute Y, as is this one. So absolute Y is the distance from the point to the XZ plane. And similarly, absolute Z, whatever the point XYZ is the distance of the point to the XY plane. Now, this is a right triangle here. Right? It's got sides, absolute X and absolute Z. So that says that this side of this triangle right here, okay, this distance here, D, D is given by the square root of absolute X squared plus absolute Z squared, or X squared plus Z squared. I mean, denote this by D1, because what I'm really interested in is this distance D over here. So D1 is given by this. And then the thing to note is that this is a right triangle here. Right? This line lies in a plane that's perpendicular to the y-axis. And so this is a right triangle right here. And so what we have then is that D1 squared, this squared, plus y squared is equal to D squared. Or that D is equals to, D1 squared is this, so we get the D squared is equals to X squared plus Y squared plus Z squared. And so the square root of X squared plus Y squared plus Z squared is going to be D. Right? So this then gives the distance from the point XYZ to the origin. Distances between the 2 points in three-dimensional space. And so if this is the point x1, y1, z1, and over here is the point x2, y2, z2, and what we can do here is we can draw rectangular parallelepiped, like so. With this point at one corner the same picture that we had here before with the point in the origin. That's to say, we want to know the length of this line segment, and to do that, we can consider triangles here. Right? This length right here is given by, I'm not drawing this in the first octant, although it's just simpler to do that rather than draw it in other ones. This distance right along here is absolute y1 minus y2. That's this distance. This distance right here is absolute x1 minus x2, and the height right here is absolute z1 minus z2. All right. So that if we consider this triangle right here, if this side of the triangle is length c, then we get this height is absolute z1 minus z2. That's squared, because this is a right triangle here. Right? Plus, that's this side squared, plus this side squared, that's absolute x1 minus x2 squared must be equal to c squared. Now the distance we're interested in here is d. Then we notice that this triangle right here is also a right triangle. So that's a right angle. This line is perpendicular to this plane, making this a right angle. So that we get d squared is equal to c squared plus absolute y1 minus y2 squared. Or d, c squared is absolute x1 minus x2 squared plus absolute z1 minus z2 squared. When we add in absolute y1 minus y2 squared, we get this. And the square root of this then gives us the distance. So this is the formula here for the distance between 2 points, x1, y1, z1, and x2, y2, z2. Square root x1 minus x2 squared, y1 minus y plus y1 minus y2 squared plus z1 minus z2 squared. Exact analog to the distance in two-dimensional space. Similarly here, the midpoint of the line segment connecting these two, this one, for its x coordinate, perhaps it's easier to do the y coordinate here, it's going to have for its y coordinate one half of the average of the two y coordinates. Similarly over here for its x coordinate is going to be the midpoint between the two x coordinates. So this midpoint is going to be located at x1 plus x2 over to 2, y1 plus y2 over to 2, z1 plus z2 over to 2. That's the midpoint of the line segment. This is the distance, huh? Between these two. Right. Now, if we wanted, we could consider a point, let's say HKL, and if we wanted to consider all the points whose distance from this point was a fixed quantity r, what we would be doing here is describing the sphere of radius r, whose center is at HKL. And a point x, y, z is going to get on that sphere if this distance from x, y, z to HKL is r. That's to say, if x minus h squared plus y minus k squared plus z minus L squared. The square root is r, or this is equal to r squared. This is a description of the, in terms of an equation, of the sphere of radius r with center at h, k, l. Okay, so we have got then three things here: the distance formula, midpoint formula, and the equation of the sphere of radius r centered at the point h, k, l. And it's just noted here, if we take a point, x naught, y naught, z naught, for example, here, we want to describe the sphere of radius r. It's centered at x naught, y naught, z naught. Its equation is x minus x naught squared plus y minus y naught squared plus z minus z naught squared is equal to r squared. Right? Just want to note at this point that conversely, if you've got something that looks like ax squared plus ay squared plus az squared plus bx plus cy plus bz plus e equals 0, right? Then this is a candidate for being a sphere centered at a particular point. And the way to find out what that is to collect the x terms together and compute the square, the y terms together and compute the square, and the z terms together and compute the square, and see what you've got. So that, for example, if we had 2x squared plus 2y squared plus 2z squared plus 3x plus 4y plus 5z plus 6 equals 0. Now I may change the 6 here. All right? What have we got here? We've got 2. Now actually we may as well divide through by 2 here, so that we've got x squared plus 3 halves x. We want to complete this square, plus y squared plus 2y plus z squared plus 5 halves z. We want to complete that square is equals to minus 6. All right. Because with this square, what we want to do is we divide this by 2. That's 3/4 and square root. So we want to add 9/4 here. So we added 9/4 to this side. We have to add 9/4 to this side in order for this to remain an equation. Divide this by 2 and square it, we get 1. We added 1 to this side, so we have to add 1 to this side right here. Divide this by 2, 5/4 and square it, we get 25/16. We added 25/16 to that side, so we have to add 25/16 to this side over here. Right, when we do this here, we're going to get something that is negative. And this is going to be a square, and this is a square, and this is a square, and it's not possible for those to add up to a negative quantity. So let's change this plus 6. That's to say there's no graph to this. If we ended up with 0 on this left-hand side, then there would be only one point to the graph. That's to say this graph looks like x plus 3 halves squared plus y plus 1 squared plus z plus 5/4 squared. If we end up with this being equal to 0, then the only point that's going to satisfy that is x is minus 3 halves, y is minus 1, and z is minus 5/4. Right? So I'm going to change this plus 6 to a minus 6 here so that we actually have a radius to this. So this is going to then become plus 6 over here. In the left-hand side of this equation, we're going to have 6 and 1 is 7. And 9/4, I guess we're going to have to change this to 16ths. So we've got 25/16. 9/4 is going to make 36/16. 7 is going to be 7 times 16/16. Or, let's see, 42. 36 is 148, 58, 68, 73. So this is 173 sixteenths, right? Or it's the square root of 173 sixteenths squared. So this is going to be a sphere. Its center is going to be minus 3 halves, minus 1, minus 5/4. So that's to say, if we let this be equal to x bar, then x bar squared plus y bar squared plus z bar squared will be equal to r squared. And x bar will be 0 when x is minus 3 halves. That's to say, this, when x is minus 3 halves, this is the x coordinate for the center of the x bar, y bar, z bar coordinate system. Similarly here, y bar will be 0 when y is minus 1. This will be a center for the system. This will be then a sphere centered at this point. Centered at this point with radius square root of 173 over 16. Or if you like, square root 173 quantity over 4. Right. So if you've got something that looks like this, it's a sphere. And similarly, a sphere of radius r centered at x naught, y naught, z naught will have an equation that looks like that. We're going to consider vectors now in three-dimensional space. And we're doing quite a bit with vectors. A vector, as in two-dimensional space, is something which has got magnitude and direction and adds by the parallelogram rule. And two vectors will be equivalent if they have the same magnitude and direction, so that these two vectors here, for example, might be equivalent to each other. And for position vectors, we place the vector with its tail end at the origin. So this might be a vector u, and here a vector v. And we're going to, just as we did in two-dimensional space, we're going to identify the vector with the tip of the vector. That's to say, the point where that's located. So the vector u will be identified with the triple u1, u2, u3, and the vector v will be identified with the triple v1, v2, v3. And now these two vectors are supposed to add by the parallelogram rule. That's to say, the result of u and v is going to be this vector right here, u plus v. Right? Now, if this was where v is, and this is where u is located, for example, here, then we want to know the x, y, and z coordinates of u plus v. Well, this vector right here is the same as u, and so perhaps the y coordinate is the easiest to visualize here. If we go over this distance here for the y coordinate of v, and then we go over this distance here for the y coordinate of u, then we should go over this distance and then again for the y coordinate of u plus v. That's to say that the y coordinate of u plus v is going to be u2 plus v2. Right? Similarly, looking at the x to z plane, right, you can note that the x coordinate is going to be u1 plus v1, and likewise from the z plane, right, looking at the z-axis here, right, you can note that the third coordinate of u plus v is going to be u3 plus v3. So u plus v then will be the vector u1 that has coordinates u1 plus v1, u2 plus v2, and u3 plus v3. We also want to be able to talk about a constant times a vector u. Right? Constant times u is going to be, if k is greater than 0, is going to be a vector with the same direction, but whose magnitude is a constant times the previous magnitude. So that a constant times u here is going to be equals to ku1, ku2, ku3. Note that the magnitude of the vector u, the vector is represented by its length here, and the magnitude is the length of the vector. This is the square root of u1 squared plus u2 squared plus u3 squared. The magnitude of ku is going to be the square root of ku1 squared plus ku2 squared plus ku3 squared, which is going to be equals to, we can take the k squared here out of the square root, giving us absolute k, and we're left with the square root of u1 squared plus u2 squared plus u3 squared, so that the magnitude of ku is equal to absolute k magnitude u. Right. Now, for k negative, in particular, for example, we want minus 1 times u to represent the negative of u. And we can then talk about subtracting two vectors just as before. That's to say, v minus u will be equals to v plus the negative of u. Okay. Likewise, for k negative, the magnitude of k times u will point in the negative direction here. If k is negative, it will point in the opposite direction of u, and its magnitude will be the absolute value of k times the magnitude of u. When k is equal to 0, then what we've got is k times u is going to be 0, 0, 0, and so what we want besides this is the 0 vector, which is 0, 0, 0. It's a vector with no magnitude and any direction that you please. Right? So you can consider this as having any direction whatsoever or no direction. Right? We want a 0 vector here. Okay, so position vectors and how they add by means of the parallelogram rule, just as in two-dimensional space and constant times a vector. Consider vector addition now, given two vectors, u, say u1, u2, u3, and v, v1, v2, v3, right? Then u plus v, oh, I suppose we can consider a third one here, 2w, w1, w2, w3, and then u plus v is defined by u1 plus v1, u2 plus v2, u3 plus v3. All right? And we want to make some sort of obvious remarks here involving rules for vector addition. So rules here. Are easily checked. First of all, you've got the commutative law holding here. U plus v is the same as v plus u. Likewise, we take u and add v to it, and then add w. We get the same thing as if we were to take u and add it to v plus w. That's the associative law. A constant times u plus v, we call it a constant times u is the vector ku1, ku2, ku3. Constant times u plus v is a constant times u plus a constant times v. We're going to want these rules because we're going to sometimes be operating with vectors. We don't want to go back to the numbers that they represent. We want to just use some algebra for them. we take two constants, c and k, and multiply this by u, this is the same thing as if we took c times u and added to it k times u. Okay? 0 times any vector u, this is the number 0, and this as before is sometimes considered to be scalar multiplication. The numbers are considered to be scalars, and you're multiplying a scalar times a vector here. Right? That's going to give you a vector, and this is, in this case, is going to be the 0 vector. Right? And then, given any vector u, there's a vector negative of u, and u plus the negative of u is the 0 vector. So here are some rules that vector addition and multiplication by means of a scalar satisfy. Let's take a look at a specific example here. Let's suppose that we let u be equal to, let's say, 3, 4, 12, and v be equal to 0, minus 3, minus 4. And then what have we got? Well, u plus v then is equal to 3, comma, 1, 8. Right. The magnitude of u, right, is the square root of 3 squared plus 4 squared, 9 plus 16 plus 12 squared, 144. 2 times u is going to be the vector 6, 8, 24. 3 times v is going to be the vector 0, minus 9, minus 12. 2u plus 3v is going to be equals to 6. 2u, we add 3v, so we get minus 1. 24 minus 12 is 12. So here then are some examples of vector addition, multiplication by a scalar, determining the magnitude of a given vector. Okay. And here are some rules that vector addition and scalar multiplication satisfy. Take a look at the dot product for three-dimensional vectors, and we've got, let's say, vector u equal to 3, 4, minus 5. We're going to want to develop an alternate notation for this vector here also, as follows. The vector in the x direction here with unit length, direction of the x-axis with unit length, is going to be denoted by I. I is going to be corresponding with the vector 1, 0, 0. The one in the y direction of unit length is going to be denoted by j. And j consequently is going to be the vector 0, 1, 0. And the one in the k direction here with unit length, the one in the z direction with unit length is going to be denoted by k. And so k is going to be the vector 0, 0, 1. And then, if u was 3, 4, minus 5, we could write u as 3i plus 4j minus 5k, and sometimes that is a nicer notation. Right? If in general here, if we've got u equals to u1, u2, u3, and v equals to v1, v2, v3, then we're going to define the dot product of u and v, like so, with the dot, to be the scalar, or number, u1, v1, plus u2, v2, plus u3, v3. vectors as before is a scalar, and it's the similar scalars to the one before. Right? And we now have some rules for dot products. Right? One, u dotted with v is the same as v dotted with u. Doesn't matter how you do this. Right here, if you take u and dot it with v, you get this. If you take v and dot it with v, you get v1 u1 plus v2 u2 plus v3 u3. They're the same thing. Right? U dotted with v plus w, this can be checked very easily, is u dotted with v plus u dotted with w. So if you like the dot product, it distributes over addition. Ku dotted with v is going to be k times u dotted with v. And it's also going to be equal to u dotted with k times v. So if you take a scalar multiple here of u and dotted with v, you get this next. So, rules here. The magnitude of a vector u now is just as before. If we take u and dot it with u, we're going to get u1 squared plus u2 squared plus u3 squared, so that the square root of that is going to be the magnitude of u. Let's take a look at an example. Let's let u be 3i plus 4j minus 5k. Let v be equal to 6i plus 7j minus 8k. Then u dotted with v is equal to 6 times 3 is 18. 7 times 4 is 28, so plus 28. And minus 8 times minus 5 is 40, so plus 40. For a total here of 68, 78, 86. So this is u dotted with v. Okay. So for particular vectors u and v, here's u dotted with v. Here, on the other hand, are some rules for vectors. One can also note that 0 dotted with any vector is 0, the number 0. We now want to look at the interpretation of the dot product and see that it's the exact same interpretation that you get in the plane. That's to say, we've got two vectors, u and v. Take a look at their dot product. We can consider this vector right here. This is the vector u minus v. It's the vector that you add to these to get to u. So if this angle right here is theta, the angle between these two, then the law of cosines, just as in the plane here, says that the magnitude of u minus v squared is equals to the magnitude of u squared plus the magnitude of v squared minus 2 magnitude of u, magnitude of v, cosine theta. This is the law of cosines. For a triangle. Okay? The magnitude of u minus v is u minus v dotted with u minus v. And this is supposed to be equals to magnitude of u squared is u dotted with u. Magnitude of v squared is v dotted with v. And so this minus 2 magnitude u, magnitude v, cosine theta. Now here we can use the distributive law here. That's to say this is equals to u dotted with u minus v dotted with u and minus u dotted with v, so minus 2 u dotted with v plus v dotted with v. Same minus v dotted with minus v. This is going to be equals to the right-hand side here, huh? U dotted with u plus v dotted with v minus 2 magnitude u magnitude v cosine theta. Now what have we got? We've got u dotted with u on this side and also on this side. We've got v dotted with v on this side and also on this side here. So we've got then, dividing through by minus 2, we've got that u dotted with v is equal to the magnitude of u, magnitude of v, cosine of theta. Just as in the plane. The interpretation of the dot product is that it's the magnitude of the two vectors multiplied together times the cosine of the angle between them. Now let's take a look at an example here. Let's suppose we've got, let's say, 3, 4, minus 5 is u, and 6 minus 7 minus 8 is v. Then, u dotted with v is equals to 18 minus 28 plus 40, or minus 10 plus 40 is equal to 30. Magnitude u is equal to square root 3 squared, well, u dotted with u if you want here, which is going to be 9 plus 16 plus 25. 25 square root of 50. Magnitude of v is equals to the square root of 6 squared, 36, v dotted with v if you want, plus 49 plus 64, or 149. Square root of 149. Now, this is the interpretation of the dot product, and so consequently, if we've got two non-zero vectors here, we can find the angle between them. Cosine of theta is equals to magnitude u dotted with v divided by magnitude u times magnitude v, which in this case right here is going to be 30 over the square root of 50 times the square root of 149. But in general, this is the cosine of the angle between two vectors u and v. It's given by u dotted with v over magnitude u magnitude v. The dot product having this interpretation. Take a look at something that can be done geometrically with vectors. Suppose we've got 3 points here. Not all on the same line. A, let's say B, and C. Where A is, let's say, given by the vector 2 minus 1, 0. B by 5 minus 4, 3. And C by, oh, let's say 1 minus 3 to 2. Now this is just a schematic here. That's to say, I'm using this schematically to represent a triangle with these 3 vertices. And what I'd like to know is the lengths of the various sides and the various angles. So that's, here I've got these 3 vectors, one ending in A, the other one in B, and the third one in C. Well, AB, the vector that goes from A to B, this vector here, I can represent like so, it's equals to this vector here is equals to the vector b minus the vector a. Take this vector b, the vector b minus the vector a is what you add to a to get to b. So that's going to be the vector from a to b. And so this is going to be equal to 3 by minus 2. Minus 4 minus a minus 1 is going to be minus 3. 3 minus 0 is going to be 3. So that from that I get the magnitude of AB is going to be square root 3 squared plus 3 squared plus 3 squared, or square root of 27. Right. BC, or AC, let's do AC. The vector AC here is the vector C minus the vector A. That's to say, the vector from A to C, if you add it to A, you get C, the vector to C. So it's equal to C minus A. So this is going to be equals to 1 minus 2 is minus 1. Minus 3 minus minus 1 is going to be minus 2. And 2 minus 0 is going to be 2. So the magnitude of AC is going to be the square root of 1 squared plus 2 squared plus 2 squared, or 4, 8, 9, or 3. So now we've got these two vectors here left, so AC and AB. Now if we want this angle here, we'll use that for illustration. It's pretty hard to get the others. That's to say, the angle at A is given by the angle whose cosine is AC dotted with AB divided by the magnitude of AC times the magnitude of AB. That's the dot product. Okay. AC dotted with AB. Right. AC is this. Here's AB. So AC dotted with AB is going to be minus 3 plus 6 plus 6. We need to divide that then by magnitude of AC, which was 3. And the magnitude of AB is square root of 27. And now the angle whose cosine is this. Cosine inverse of this quantity is the angle at A. That's to say the angle at A is cosine inverse of 6, 12, 9 over 3 square root 27. Or simplifying here, 1 over square root of 3. 9 and 3, and square root of 27 is 3 square root of 3. So this gives you then the angle at A. Here's the magnitude of AB. And here's the magnitude of AC. And clearly you could do the rest of this. You could find all the angles and sides of this triangle if you knew the points where the vertices are. Now I want to take a look at what I call the direction angles for a vector. These are sometimes of use. And they're an interesting situation going for them. This is the X, Y, Z axes respectively. And this is vector U. Right. Then the angle of U with the x-axis is denoted by alpha. And the one with the y-axis is denoted by beta. And the one with the z-axis is denoted by gamma. Right. And so if our vector U was equals to U1, U2, magnitude of I cosine alpha. That's to say cosine alpha is equals to u dotted with I over magnitude u, which is equals to u1 here over magnitude u. Similarly, u dotted with j is going to be magnitude u. Magnitude j is 1 cosine of beta. So the cosine of beta is equals to u2 over the magnitude of u. And finally here u dotted with k is equal to magnitude u times magnitude k, which is 1 cosine of gamma. So the cosine of gamma is equals to u3 over magnitude u. All right. Now, an interesting relationship between these angles here is the following. Cosine squared of alpha plus cosine squared of beta plus cosine squared of gamma is equal to what? Because what? Cosine squared of alpha is u1 squared over magnitude u1 squared plus cosine squared of beta is u2 squared over magnitude u squared. u1 squared over magnitude u squared. u2 squared over magnitude u squared plus u3 squared over magnitude u squared. That's cosine squared of gamma. This is equal to u1 squared plus u2 plus u3 squared over magnitude u squared, which is equal to 1. This is the analog of the plane situation here, where if you've got an angle theta, right, then sine squared theta plus cosine squared theta is equals to what? Well, if this was theta and this was phi, then sine of theta is cosine of phi. And so what we actually have here is cosine squared of phi plus cosine squared of theta is equal to 1. In the plane, that's another way of saying sine squared plus cosine squared of a given angle is 1. So here in three-dimensional space, it's the relationship between the cosine angles. Cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. And now, it's also possible to write the vector u as follows. U is equals to cosine alpha times magnitude u times I, right? Cosine alpha magnitude u is u1. So cosine alpha magnitude u I plus cosine beta magnitude u j plus cosine gamma magnitude u k. Right. Also the vector cosine alpha I plus cosine beta j plus cosine gamma k is a unit vector in the direction of u. Cosine alpha I plus cosine beta j plus cosine gamma k is a unit vector in the direction of u, and so consequently it's equals to u times 1 over the magnitude of u. It's another way to write a unit vector in the direction of u. Okay, so sometimes it's handy to use these direction angles for a given vector u. Well, look at the component of a vector u in the direction of another vector say, if this is a vector u here, and this is a vector v, and we want to know what's this magnitude right here. If we take u and project it perpendicularly here to v, and we get that that should be equals to magnitude u cosine theta. This we're going to write as the component of u in the direction v. Right? But now, using the dot product here, we get that the dot product of u and v is magnitude u, magnitude v, cosine theta. So that if we divide this by magnitude v, we're going to get the component of v in the direction of u. Now, similarly here, as in the plane, we can write u as two parts. One is this vector here, and the other one is the vector in this direction here. One is the vector in the direction of v, and the other one is the direction, the one perpendicular. So the parallel part right here to v, and if it's not clear what's meant, v should perhaps be indicated here. This is going to be the vector that has got magnitude component of u in the direction of v. That's to say, u dotted with v over magnitude v is going to be the magnitude of this vector. And so if we take this magnitude and we multiply it by a unit vector in the direction of v, a unit vector in the direction of v is given by v divided by magnitude v. Well, that's to say, v times 1 over magnitude v. This is a vector in the same direction as v, but with unit magnitude. So that this right here then is the parallel part of u in the direction v, right? Or u dotted with v over magnitude v squared, or v dotted with v times v. So that this is a dot product, so that's a scalar. This is another scalar here, and so that we're taking a scalar and multiplying it by a vector, giving us a vector here. This is u parallel to v. And the remaining part is going to be the perpendicular part. That's to say, if we take u and we subtract off the parallel part, we're going to get the remainder of u, which is going to be perpendicular to v. That's to say, this is going to be u minus u dot v over v dot v v. As in the plane, two vectors a and v are perpendicular if and only if the dot product of a and b is equal to 0. That's because the dot product is the magnitude of a, magnitude of b, cosine of theta. If they're perpendicular, theta is 90 degrees, or pi over 2, cosine theta is 0. And so if they're perpendicular, then the dot product is 0. If the dot product is equal to 0, then either one of them is 0, and we can consider the 0 vector to be perpendicular to any vector if we wish. Or if neither of them is 0, then the cosine of the angle theta is equal to 0. Now, it's easy to check here that if we take, just as before, if we take the dot product of u parallel with u perpendicular, we get 0. So that these are the two components of u. One in the direction of v and the other one perpendicular to it. An interesting application of this perhaps is to work. If you imagine pushing a lawnmower with a force in this direction here, cross a distance d in this direction here, the work involved in doing this is the component of the force in the direction of the distance, that's to say magnitude F cosine theta, times the magnitude of the distance. The force has got two components, one in this direction and one that's going down into the ground, which doesn't do any work at all. It's the force in the direction of the distance that gives rise to the work. So this is the work right here, and so it's clear then that the work is the force vector dotted with the distance vector. Right? Which the dot product of force with distance is going to be magnitude force, magnitude of the distance times the cosine of the theta, of the angle theta. So for a force involved in pushing an object across a distance, where the force is not in the same direction as the distance, the dot product of force with distance here gives you the work. Okay? So here's one place where this can be used, and the component of u in direction of v, the parallel part, and the perpendicular part. Now I want to look at the product of two vectors, which really only works in three-dimensional space. And it's called the cross product. And if you've got two vectors here, say u1, u2, u3, I want to take the cross part of that with the second vector, v1, v2, v3. This is going to produce a resulting vector. This is going to have three components. The I component, or the first component, is going to be u3 v1 minus u1 v3. The J component, or second component, is going to be, oops, the first component is going to be u2 v3. I'll explain how to get these in a minute. We have to get them right first. Minus u3 v2. So u2 v3 minus u3 v2. The J component is going to be u1 v2. I'm sorry. u3 v1 minus u1 v3. And the K component is going to, the third component is going to be u1 v2 minus v1, u2 v1. Okay, that looks a little bit mysterious at this point if you haven't seen it before. But the basic idea is something like this. If this can be remembered, if you want, by considering a sort of a circle that goes like this. I, J, K, and back around to I. That's to say, I crossed with J is going to be K. J crossed with K is going to be I. And K crossed with I is going to be J. Right? And this cross product doesn't commute. In fact, what it does is anti-commute, so that if we take I cross J, we get K. This is going to be the negative of J cross I. J cross K is I. K cross J is the negative of I, or this is minus K cross J. K cross I is J. This is minus I cross K. Right? I cross I, J cross J, and K cross K are all equal to 0. That's to say the zero vector. The cross product of two vectors is always going to be a vector. Going around I, J, K here. Right? Also what happens is this. We take three vectors, U, V, and W. U crossed with V plus W is going to be equals to U crossed with V plus U crossed with W. Right? And also a constant times U crossed with V is going to be equals to a constant times U crossed with V. Right? Now, let me show you how I got this here, and I'll show you an alternate way of getting it, but I consider this to be pretty straightforward. This is these, you're going to get the negative of what you would get otherwise. So for the I component up here, right, I want k, j crossed with k, or that's to say u2v3, and I want the negative of k crossed with j. So minus u3 v2. That's going to give me the I component. That's what's sitting right here. Right? For the j component, to get the j component, here I have to take k crossed with I. So that's to say u3 v1 minus I crossed with k is u1 v3. So this is the j component. The k component is going to be given by I crossed with j. That's to say u1 v2 and minus j crossed with I, minus u2 v1. So that's the k component. So there's the resulting vector. Here it is up here. And you can do this by just keeping track of what's supposed to go where. Right? Some people like to do something like the following. For u1, u2, u3, v1, v2, v3, and I, j, k in a matrix and compute the determinant of this matrix. Right? Some people like to put the I, j, k on the top and then u1, u2, u3 down below. You're going to get the same result if you do that. So to compute the determinant of a matrix, what you do is you go across, let's say, the first row here, and you assign these alternately plus, minus, and plus signs. And so we get that the determinant of this is going to be u1 times the determinant of what's left when you remove the first row and first column. That's to say, the row that contains u1 and the column that does. So this is going to be v2, v3, j, k. And the second element here is negative, and so we get minus u2, and the determinant of what we get if we remove this column and this row. That's to say v1, v3, I, k. And then finally plus u3 times the determinant of what we get if we remove this row and this column. That's to say v1, v2, ij. Now we need to evaluate these determinants, and for that purpose we put plus and minus sign in here. This is a general way of evaluating determinants. Larger determinants can be evaluated in this way by putting plus minus across the top and computing the constant times the determinant of what you get if you delete its row and column. Okay, so what do we get here? We get u1, and then this is plus v2k. Right? And then it's the determinant of k is of an element is itself. And we get minus u1 v3 j is what's left over. So we get then minus u2. This is in the plus position, so it's v1 k. Remove the row and the column. Huh? Minus times minus is plus u2 v3 I. Here we've got u3, so we've got plus u3. We have v1 j. And then we've got plus u3 times minus, so it's going to be minus u3 v2. We remove this, we get I. Right? Now, that should be the same. U cross v. It's readily checked that it's going to have the same, for example, I coordinates. Here this is u2 v3 minus u3 v2, and so forth. So either by means of evaluating a determinant or just computing directly, one can get the cross product of two vectors. Now I want to take a look at some properties of the cross product. In particular here, if you've got vectors u a couple of these properties, but basically they all consist of checking to make sure that the algebra works out right, coordinate by coordinate. For example, KU crossed with V, this is KU crossed with V, is K U crossed with V, which is equals to U crossed with KV. And it's just simply a question of taking a constant K, multiplying it by U, crossing that with V, and checking to see that you get the same thing as if you take U crossed with V, and multiply by K, and again you get the same thing if you get U crossed with what you have when you take K and multiply it by V. So we won't check that one particularly. We'll only check one of these. U crossed with 0, U is always the 0 vector. Take any vector U, cross it with itself, and you're going to get the vector which is identically 0. Right? That's easily checked. You take U crossed with V, and dot this with W. This gives you a vector, the cross product gives you a vector, and you dot that with the vector W. This is the same as what you get if you take U and dot it with V crossed with W. So if you interchange the cross and the dot here, you get the same quantity. This quantity right here is sometimes called the triple scalar product. Because it takes 3 vectors and it gives you a scalar as a consequence. Okay. U crossed with V crossed with W. Right? Or actually, let's do a more illustrative one first here. Let's take a look at U crossed with V dotted with U. This is a special case of the one above here, and we get that this is equals to U well, actually let me change this around. Let me make this V crossed with U dotted with U. Right? This is going to be equals to, by the above here, it's going to be V dotted with U crossed with U, which is going to be 0. Okay. Likewise, if we put V on this side here and we dot it with V crossed with U, right, we get that this is equals to, using this formula again, V crossed with V dotted with U. V crossed with V dotted with U, right? Which is going to be also equal to 0 because V crossed with V is 0. Any vector crossed with itself is going to be the 0 vector. U crossed with U is 0. So the conclusion that one reaches here is that V crossed with U here, since it's dot product with U is 0, that this is perpendicular to U. And V crossed with V dotted with V crossed with U is 0, so that V is perpendicular to V crossed with U. So what the vector V crossed with U gives you is a vector which is perpendicular both to U and to V. Right? If U and V have the same direction, if let's say if U is a multiple of V, then U crossed with V is going to be 0. But otherwise you've got the cross product resulting in a vector which is perpendicular to both the vectors involved in the product. Right. U crossed with V crossed with W. Okay. This is a formula that's sometimes useful. Basically, you'd expect this to be perpendicular to both u and v crossed with w is going to be perpendicular to v crossed with w. That means it should lie in the plane that's determined by v and w. And this is a help to remember what this is. That's to say, this is equals to, it's got a v component and it's got a w component. And the v component is u dotted with w. And the w component is minus u dotted with v. So this is a formula here now, and it can be checked by basically taking u, v, and w here and seeing that algebraically you get the same thing. If you take v cross w, cross that with u on the left, and compare it to what you've got on the right-hand side here. Right? A formula which is even messier still is the magnitude of u crossed with v. This squared is equal to the magnitude of u squared, the magnitude of v squared, minus u dot v squared. Right? That's to say, if you put these, put u and v in here, and you compute this left-hand side here, and you compute this u dotted with u, and v dotted with v, right? And u dotted with v and squared, subtract this, you get the same number now here. Both sides of this equation are numbers. Now, this turns out to be important here, because from this, you can get more information about the cross product. Namely, the magnitude of u cross v squared is equal to magnitude u squared, magnitude v squared. Now, u dot v is magnitude u, magnitude v, cosine theta. So that we get that this is equal to magnitude u squared, magnitude v squared, cosine squared theta. So we've got this right here. So we now have that u cross v, the magnitude of it, is equals to magnitude u, magnitude v. What have we got? We've got 1 minus cosine squared theta here is going to be sine squared theta, and the square root of sine squared theta is going to be sine of theta. So what we find out here is a very important formula, namely that the value, the magnitude of the cross product is the product of the two magnitudes times the sine of the angle between the two vectors u and v. Right? So this basically tells you almost completely what happens when you take a cross product. The resulting vector is perpendicular to the two vectors u and v, perpendicular both to u and to v. Right? And its magnitude is the product of the two magnitudes times the sine of the angle theta between the two vectors. Right? The cross product also obeys the right-hand rule in the sense that if we take u and we cross it with v, the resulting vector u crossed v is going to be what you get if you started at u, went the shortest direction to v, and with your fingers, and then u cross v is going to be the direction of the thumb of your right hand. Okay. Let us check this right here. U crossed v. All right? And we want to dot that with w. So what happens here? Let's check it over here. U crossed v is what? Its first component is going to be u2v3 minus u3v2. The second one is going to be the j component is going to be u3v1 minus u1v3. Right? Its k component is going to be u1v2 minus u2v1. So there's the Now, if we dot this with W, what do we get? We get, here's the vector here, W1 U2 V3 minus W1 V3 U3 V2 plus W2 U3 V1 minus W2 U1 V3 plus W3 U1 V2 and minus W3 U2 V1. So this is what we get for a total here. If we now take this and dot it with W, right? What happens if we take V cross W? Well, we've got the same thing here, except that V replaces the U, and W replaces the V. So the same formula here, except that we can read the U as a V and the V as a W. Now we take U and dot it with that. And what do we have? Well, we've got U1, and then we've got V2 W3 minus U1 V3 W2. Right? And then we've got U2. Right? V3 W1. And then we've got U2 minus U2 V1 W3. Then finally we've got U3 V1 W2 minus U3 V2 W1. Right? So here's what we get if we perform this in the other direction. Now what we want to do is we want to show that these two things in the squares are equal. Well, what have we got here? It's just a question of checking. Here's U1 V2 W3. Here's U plus U1 V2 W3. Here's minus U1 V3 W2 minus U1 V3 W2. Right? Here's U2 V3 W1, U2 V3 W1 minus U2 V1 W3, U2 V1 W3, U3 V1 W2, that's right here, and finally U3 V2 W1, U3 V2 W1 with a minus sign. So that we've just checked the fact now that U cross V dotted with W is the same as U dotted with V cross W. Right? And the rest of these things check in exactly the same way. That's to say, basically do the algebra that's needed to compute them and see that you get the same expression on both sides of the equation. We're going to want to look at functions R of t, which describe curves in space here eventually. And the simplest of these curves are going to be lines. And in particular here, if we take a point, R naught, or R naught is x naught, y naught, z naught, it's that vector, and a direction here, B, where V is equal to ABC, then this determines a line through the point having the direction V. And R of t can be given describing that line as follows. R of t is equal to R naught plus t times V. That's to say, any point gets on this line, if you can get to it by going first to R naught and then adding on to that some multiple of V. That's to say, R of gives you parametric equations here, x, y, and z of t, and it gives you also then a vector value function of t, which describes this line. It does so in a somewhat interesting fashion here. All right? That's to say, when t is equals to 0, when dealing with this point right here on the line, when t is equals to 1, one adds on the quantity a here, and so this is 1. When t is minus 1, 1 is back in this direction, so this is where minus 1 goes. Minus 2 goes back here. 2 goes another unit in this direction like so. Right? And so what this parametrization does is it places on this line a copy of the real numbers with 0 at the vector r0, 1 at r0 plus v, and the various other numbers along the line like this. Okay. So here what we've got here is the following situation. Given a point in a direction vector, right? There's one line through the point with the direction. Now, usually, instead of given a point in a direction vector, you expect that if you're given 2 points, that there's going to be exactly one line that goes through those 2 points. So, if here we're given 2 points here, R0 and R1, we would like to know what is the line through those points. So given 2 points, right, or given a point in a direction vector, we expect one line through the 2 points. Well, if this is R0 and this is R1, we can then get a direction vector like this. The direction vector V will be R1 minus R0. R1 minus R0 was the vector you add to R0 to get to R1, and so that's going to be a direction vector. So in the case here where we're given 2 points, you can write R of t as R0 plus t times R1 minus R0. Now, if R1 is the vector x1, y1, z1, then the parametric equations here, or the coordinate equations of this vector valued function, are going to be x of t is equals to x0 plus t times x1 minus x0, y of t is equal to y0 plus t times y1 minus y0, and z of t is going to be z0 plus t times z1 minus z0. Another thing, one thing to note here is that when t is equal to 0, the point that's on the line is x0, y0, z0. When t is equal to 1, the point is going to be x1, y1, z1. When t is equal to 1, we're going to get x1 minus x0 plus x0, or x1, likewise y1 and z1. So, given 2 points, right, there's a line through them, and it can be parametrized like so. But given a point in a direction vector, that's really the way in which you think of this. You can parametrize it like this. Next, I want to know how to represent planes in 3-dimensional space. And given a point in the plane, when we attach it to, and draw the line segment to R naught, these two will be perpendicular. That's to say this vector n is perpendicular to the plane. So that what happens here? If we take a vector x, y, z in the plane, right, any vector like so, then if we wish to describe this plane, if this is the general vector r, then r minus r naught should be perpendicular to n. So this dotted with n should be equal to 0. Alright? Now we're going to write this out. We'll find that a plane has a single equation in x, y, and z. R is x, y, z. R naught is x naught, y naught, z naught. It's a fixed point. And this dotted with a, b, c is supposed to equal 0. Take this, dot it with a, b, c, we're supposed to get 0. Well, what is this? This is x minus x naught, right, times a, that's the x coordinate here, do the dot product, plus y minus y naught times b, z minus z naught here, times c equals 0. I multiply this out here, we get ax from this plus by plus cz, that takes care of these three terms here, is equal to, I'll bring this to the right-hand side, ax naught plus by naught, so we got minus y naught times b, bring that to the right-hand side, plus cz naught. Right. So you can remember this, if you like, as the equation of a plane through x naught, y naught, z naught, having a, b, c as a normal vector. Sometimes this last quantity here is just simplified and called d, and so you write ax plus by plus cz equals d, or sometimes the form of this is given as ax plus by plus cz plus d equals 0 is the equation of a plane. Okay. Now, you expect not just to have a point and a normal vector here determined in a plane, but normally 3 points determine a plane. There's exactly one plane that goes through 3 points. So if we have R0, R1, and R2, not all on the same line, we expect that those 3 points are going to be determined a plane like so. It lies on the 3 points. What's the situation there? We've got R0, R1, and R2. Well, these do not all lie on one line. And we wish to determine the plane. Go back to this case here and try and find a normal vector. One way to get a normal vector here is to do the following. Take the vector R0 minus R1. That's this vector right here. It's the vector that you add to R1 to get to R, I suppose let's do, yes, to add this to R1 we get to R0. Take the vector R2 minus R1. That's this vector right here. It's the one that you add to R1 to get to R2. If we now take their cross product, this is going to be a vector which is perpendicular to both of these two, this one and this one. So it's going to be perpendicular to both of them, and so that it can serve as a normal vector. If we compute the cross product here, we can treat this as a normal vector, And now any point R, a general point R, equal to x, y, z, will get to be on this plane if r minus r naught, for example, dotted with this is equal to 0. Now all that remains is to take these 3 points here, do this cross product, take the dot product with the general point, r minus r naught, set it equal to 0, and you'll have an equation for the plane. This takes a little bit of work, but it's really nothing more than arithmetic. Let's take a look at a simple example of the first type here. Let's suppose that our point r naught is 1, 2, 3, and that our normal vector n is equal to, let's say, 4, minus 5, 6. Then what's the equation of the plane? Well, it's going to be 4x minus 5y plus 6z, that's ax plus by plus cz, is equals to n dotted with r. Right? That's to say 4 minus 10 plus 18, or 22 minus 10, 12. So the equation of the plane that goes through this point, and hence this is a normal vector, is 4x minus 5y plus 6z is equal to 12. Right. Given a position vector and a normal vector, computing the plane is perpendicular to the normal vector and through the position vector is simple. Given 3 points, one can get a normal vector by taking a cross product, in this case like so, choosing 2 pairs of them like so and taking the cross product. And then once you have a normal vector, then it's also easy to write the equation of the plane. We want to take a look at the intersection of 2 planes now. And generally, given 2 planes, they're likely to intersect. So that if we've got ax naught, ax, let's do a0x plus b0y plus c0z is equal to b0, and a1x plus b1y plus c1z is equal to b1. This is going to describe 2 planes, and the normal vectors to these planes, the 0 normal vector here is going to be a0, b0, c0, and the normal vector to the other plane, and 1 is going to be a1, b1, c1. And the only way in which these 2 planes are not going to intersect is if they're parallel, and if they're parallel, then the normal vectors will be parallel. That's to say, one normal vector will be a constant times the other. So n1 is some constant times n0, and they're parallel. Otherwise, they're going to intersect. And if they intersect, there's essentially 2 possible ways to deal with that fact. We want to find the line where they intersect. One is to find one point on the line and a direction vector. And one way to get the direction vector is the following. We've got these 2 planes that intersect. If we take n0 and cross it with n1, this is going to be perpendicular to both n0 and to n1. And so this will serve as a direction vector. It's going to be perpendicular to n0, it's going to be perpendicular to n1. And so if the 2 planes intersected along this line here, this perhaps is the normal vector to one, and this is the normal vector to the other, then the direction vector can be found by finding a vector which is perpendicular to both of these 2, n0 and n1. perhaps also at this time worth noting the following. If we've got two planes, and let's look at them lengthwise here. So if this is plane 1, and this is plane 0 here. And if this is the normal vector here to this plane, and 0, and this is the normal vector here to the other plane, and 1, then the angle between the two planes here, when you look at them lengthwise like that, is going to be the same as the angle between the two normal vectors. So that we get that the angle between the planes, right, can be gotten by taking n1 dotted with n2, right? This is going to be equal to magnitude n1, magnitude n2 cosine theta. So if we divide this by magnitude n1, magnitude n2, we're going to get this is cosine theta, where theta is the angle between the two planes. They have two choices for cosine theta, either the smallest of the two or the larger of the two here. This is, of course, pi by this theta, and the cosine of pi by this theta is the same as the cosine of theta. So you can find the angle between the two planes like so. Let's take a look at an example as to how to do this by finding 2 points on them. Here we can find a point in the direction vector by using the cross product. Right? If we find 1 point in the direction vector, let's take a look at how to find 2 points. Right? Let's suppose that we've got 2 planes. Let's say 3x plus 4y plus 5z is equal to 6, and 7x plus 8y plus 9z is equal to 10. Right? Well, any point will lie on these 2 planes together here if it satisfies both of these equations. So what we can do is try and solve these equations simultaneously. Right? Here, for example, we can eliminate the y variable from both of the equations. If we simply multiply the first equation by 2, 6x plus 8y plus 10, z is equal to 12, and subtract here, in which case the y disappears and we get x minus z is equals to minus 2. Right? So now, what happens is this. We want to find points x, y, z that satisfy these 2 equations here. Right? And we found that if we take any x and z, so that x minus z is minus 2, we can find a y so that the triple will satisfy the equations. In particular, for example, let's suppose we let x be equal to 0 and z then be equal to 2. Right? If we let x be, also if we let x be equals to, let's say 1, and z equals to 3, then x minus z will be minus 2. Well, if x is 0 and z is 2, what happens here? We get 3 times x plus, in this case right here, we get 3x, x is 0, plus 4y, plus 5 times z, which is minus 2, is supposed to equal 6. Or altogether we get here, 4y is 16, y here is equal to 4. So we've now found a point here that belongs to both of these lines. Right? It's easy to check that it does. We've really just checked the first one here. And now if we take the second, we've got 0 plus 2 times 8. 4 times 8 is 32. It doesn't. Let's check our work here. All right. If x is equal to 0 and z is equal to 2, we then have 3 times 0 plus 4 times y. This is 5 times 2. Right? So that we get 10 plus 4y is 6, or 6 minus 10. 4y is minus 4. Y is minus 1. Okay, we now can check. Y is equal to minus 1. x is 0, z is 2. All right, it should satisfy this one because we just did that. How about the second? When x is 0 and y is minus 1, we get minus 8. Z is 2, so we get plus 18 equals 10. So that checks. Right. Let's find the second point here now with x equal to 1 and z equals to 3. So if x is equal to 1, for example, here we get 3 times 1 plus 4 times y plus 5 times 3, z is going to be 3, is equal to 6. So altogether here we've got 3 and 15 is 21. So 4y is equal to 6 minus 21, or minus 15, and y is equal to minus 15 over 4. So y equals minus 15 over 4. Right? So we now have 2 points here. The first one is 0, minus 1, 2. The second one here is 1, minus 15 over 4, 3. Both of those are on the line, so consequently we can write the equation of the line x, y, z, right, minus one of these points, let's say 0, minus 1, 2, right, times t, right, this is r minus r0, minus r0 is equals to t times the direction vector. And the direction vector we could get by subtracting these two. So that, for example, a direction vector here is going to be 0, minus 1, minus 1 minus 15 fourths. That's to say 15 fourths minus 4 fourths, or 11 fourths. And 2 minus 3, or minus 1. Right? So that here then is an equation of the line. The parametric equations are x minus 0 is equal to minus t, y plus 1 is equal to 11 fourths t, and z minus 2 is equal to minus 1 t. So there's the equations for the line given the 2 points, which is perhaps easier. It's easier to find perhaps the 2 points than to take the 2 normal vectors and take the cross product to get a direction vector. However, perhaps they're just about as easy in most cases. You now want to take a look at where a line intersects a plane, or where 2 lines can intersect each other. And given a plane, let's say ax plus by plus cz plus d equals 0, and a line, let's say x is equals to x naught plus 8t, y is equal to y naught plus bt, and z is equal to z naught plus ct. It's really likely that a plane, a given plane and a line, are going to intersect. Right? It's of course possible that they not intersect. However, you can find this very simply by simply solving these 4 equations here in 4 unknowns. That's to say, x, y, z, and t are all unknowns here. The rest are given constants. And it's not difficult to do that if you approach it in the correct fashion. That's to say, if you first solve for t, let's take a look at an example. Let's suppose we look at x plus 2y plus 3z is equal to 4. And now let's suppose that x is equal to 1 plus 5t. Say y is equal to 6 minus 7t. And z is equal to 8 minus 9t. Okay? What we can do is we can solve these equations here. Well, actually, we can put these equations in x, y, and z. This is the line. We can put them in here. In which case, what are we going to get? We're going to get 1 plus 5t plus 2 times y, 6 minus 7t, plus 3 times 8 minus 9t is equal to 4. Okay? So now, what have we got? Well, we've got 5t minus 7t is minus 2t, minus 9t is minus 11t. That's the t quantity. 5 minus 7 minus 2 minus 9 is, oops, let's do this correct. 5 minus 2 times 7 is 5 minus 14 is minus 9, minus 3 times 9, right, is minus 4 times 9, or minus 36. Let's check. We've got 5 minus 14 minus 27t, or minus 9 minus 36t. Right? For the constant terms here, we've got 1, and 12 is 13, and 24 is 37. So we've got 4 minus 37, or minus 33. Right? So, checking this, we've got 1, and 12 is 13. 13 and 24 is 37. We have minus 33, so it gets t is equal to 33 over 36, or 11 over 12. Once we've got t here now, we then have x is equals to 1 plus 55 over 12, 5 times t. Y is equals to 6 minus 77 over 12, 6 minus 7 times t, and z is equals to 8 minus 9 times 11 over 12, and this gives us then the point x, y, z, where the line and the plane intersect. Right, so solving the equation for the plane with the 3 equations for the line, the parametric equations, gives you the point of intersection. Right. Now, if you've got 2 lines, right, it's possible that they'll intersect, but you wouldn't expect it. Right? If we've got this first line here that's given like so, and we've got another line here that's given by x is equal to x1 plus d, and now instead of t here, I'm going to use a different letter s, and y is equal to y1 plus es, and z is equal to z1 plus fs. Right? It's important to use a different letter here. If you use the same letter, then you've got this parametrization in terms of t here, and this parametrization in terms of t here, and you really ask whether these 2 parametrizations collide. Now, if that's what you want to know, then instead of s here, use t and solve these 6 equations in essentially, if you're using t, 4 unknowns, x, y, z, and t. Right? Here, however, you've got 6 equations in 5 unknowns. Right? The unknowns are x, y, z, t, and s. Right? If you can find the solutions to them, and it's not likely that this many equations in 5 unknowns will have a solution, but if they do, then the solution to those equations is the point of intersection of the 2 lines. Otherwise, which is most likely the case if these lines are taken random, they're not likely to intersect. Okay, so the intersection of a line and a plane, very likely. You've got 4 equations and 4 unknowns. The intersection of 2 lines, not very likely, but here's how to find it. I want to say one last thing about the cross product, and that is that it's sometimes used for its geometrical significance. If we look at 2 vectors u and v, and we take u cross v, the magnitude of this is the magnitude of u times the magnitude of v times the sine of the angle theta between them. So that the 2 vectors here are u and v. theta is this quantity right here. Magnitude u sine theta is that quantity right here. And so consequently, interpretation of the cross product, the magnitude of the cross product, it is the area, this is the area of the parallelogram. Right? Determined by u and v. Right? Well, that can be used for geometric significance sometimes. In fact, a lot of areas can perhaps be computed by breaking things down into parallelograms. Or if you want, 1/2 of that magnitude is the area of this triangle. So that areas of triangles in free space can be computed using the magnitude of the cross product.